I'm making a video of the class lecture notes for November 15th with my rotation 5. And the purpose of the video is I can share it with my virtual students also so that you can complete the assignment that says that you have to turn in class lecture notes. So I'm going to share my screen. We're going to go over some class lecture notes today, and then by tomorrow, if you can drop your class lecture notes in here. It says the assignment is only for in-person students because I was thinking that the in-person students would be the only ones who can see this. However, because I'm making the video, I'd like my virtual students also to take notes and submit them. So there we go. I can write on this whiteboard. First things first, how far is the sun from the Earth? Thoughts? Very far. So I got the sun right here. And I have the Earth right here. This is Mr. 150 million kilometers. How did you know that, young sir?
Oh, what guess?
Man, lucky had nothing to do with it. You had brains. Very good. So Paul just gave us the answer. I like it. 150 million.
Right?
Yes, 150 million kilometers. And of course, you can write it as 150 times 10 to the 6 kilometers. So just like 1 gram, when they were coming up with the mass of 1 gram, they compared it to water. They said, what is the mass of 1 milliliter of water? If you take 1 milliliter of water or 1 cubic centimeter of water, and you find its mass, whatever that mass is, we're going to call that the gram. From there onwards, they called it a gram. So same thing over here. They have to compare it to a set standard. And Earth's orbit around the sun is almost a perfect circle. It's almost a perfect circle. So we're going to use that as a standard to compare our other planets' distances to. And we're going to call that an astronomical unit. So the distance the Earth is from the sun, 150 million kilometers. We're going to call that one astronomical unit. So from now on, if a planet is 300 million kilometers, we'll just call that 2 astronomical units because it's twice the distance from the Earth to the sun. So this is going to be called 1 AU. AU stands for astronomical unit. So the standard they're using is the distance between the Earth and the sun. Even though the orbit is a little bit elliptical, it's very close to being a perfect circle, so the distance from the sun stays pretty consistent. All right, sometimes you hear the Earth, sometimes you hear people refer to the moon as a celestial body. Sometimes they refer to the Earth as a celestial body. Why do they use this term celestial body? Where does it come from? Think about your assessment, your recent assessment and section reading assignments that I gave you. Did the term celestial show up in any of those reading assignments? Yeah, there's a celestial sphere, right? Which is a globe. We thought there was a globe around the Earth where all the planets, all the stars were in that globe because that's what we thought was the universe. And so an ecliptic is like the distance that the sun travels on that celestial sphere. So that's why people can call the moon a celestial body, a body in the celestial sphere, even though we know that the celestial sphere isn't the end of our universe. We just thought it's a globe around the Earth. Our universe goes past it. But when you're looking at the stars and you're sitting on the ground and you don't have a telescope, then you think that there's a globe around us and all the stars fit in that globe, which we call a celestial sphere. So sometimes you can call these planets celestial bodies, and that's okay to do that. Okay, dokie. So let's talk about Kepler's 3 laws. Kepler had 3 laws. What was Kepler's first law? Every planet's orbit in our solar system around the sun, every planet in our solar system, it orbits around the sun. Their orbits are ellipses. Very good. Their orbits are elliptical. Earth's orbit is very close to being a perfect circle. Mars is quite elliptical, quite noticeably elliptical. So you're absolutely right, Lucy. Kepler's first law is that all the orbits for all the planets in our solar system are elliptical. They have elliptical orbits. So what is an ellipse? How do you define an ellipse? How do you define an ellipse? Very good. It's an oval or an egg shape. How many focal points does an ellipse have? It has 2 focal points. And on the screen, I'm drawing these in black. They're 2 focal points. Your textbook does a very good job of saying, look, you can draw an ellipse very easily if you take 2 push pins, a string, and a pencil. So they say, look, these 2 black dots that I've drawn here, the focal points, imagine if they're push pins. And you push them into a notebook or into the wall. And then you take a string and you wrap the string around. And you take a pencil, and right here is the pencil. And you keep the string nice and tight. Now, whichever direction you move in, whether you move towards the right or to the left, that pencil is going to form an elliptical path for you. So that little dot here, maybe I'll put the dot in a different color. Let's put it in green. Right here is the pencil. And the string is wrapped around the pencil, and it's wrapped around the 2 black push pins, the 2 focal points. And so as you move the pencil, the string remains pretty tight, and it'll create an ellipse for you. And you'll notice that the distance, if I label this distance L1, the distance over here, and I call this one L2, then the sum of L1 plus L2 is always going to be the same. It's always going to be constant. That's one of the traits of an ellipse. So an ellipse has 2 focal points, and this is one way you can draw it. Can everybody picture what the book was saying about a pencil within the string? Then the book went a little bit further and said, okay, look, if you find the center of this ellipse, the distance from the center to the outer edge is called the semi-major axis. And whether it's on the right side or it's on the left side, the distance from the direct center to the outermost edge of the ellipse is called the semi-major axis. So what do you suppose is the major axis? The major axis is just simply this entire distance. If you would do the entire distance, that's called the major axis. So this in green, this is the entire distance, that's the major axis. The halves of that, the half amount of that are called the semi-major and the semi-major axis. So this half is called the semi-major, this half is called the semi-major, but the whole thing, all in all, is called the major axis. So that's the horizontal longest sides of the ellipse. By the way, this side, the vertical side, is called the minor axis, and each half can be called a semi-minor. The top half would be semi-minor, bottom half would be semi-minor. Right now, you don't need to know that. I think semi-major is most important. So you're absolutely right. Lucy said it. Lucy said Kepler's first law. So Johann Kepler had 3 laws. His first law says that all the planets in our solar system, their orbits are elliptical. All the planets have elliptical orbits. So what happened was his mentor, Johann Kepler's mentor, thought that the planets' orbits were all circular. And the mentor could not figure out the data for Mars. Mars gave a certain amount of data that could not fit a circular orbit. So the mentor gave that data to Johann Kepler, thinking Johann Kepler would fail and look bad. So the mentor was a little jealous of Johann Kepler. But Kepler came back and he said, well, I've figured it out. It's because the planet's orbits are not circular, the planet's orbits are elliptical. And Mars's data, all of the data collected by astronomers about Mars's movement, fits the elliptical path perfectly. So then Kepler was able to change the laws of planetary motion and say, look, the first law has to be that the planet's orbits are all elliptical. They're all ellipses. All right, can I erase this? What was the second law? Mr. Johann Kepler had a second law.
Something about the line sweep at the same time.
Ooh, very good. Very good. So I don't know why I'm getting these blue dots on my screen, but if you have an ellipse, and I'll draw a nice best I can. And for our ellipse, at one of the focal points is the sun. So one of the focal points right here, we'll do the Earth's orbit. There are 2 focal points. There's nothing at the other focal point, but at one of the focal points, there's a sun. And we'll talk about the Earth. So the first thing he said was that when the planet is further away, if this is Earth, when the planet is further away from the sun, is it traveling faster or is it traveling slower? Yeah, when it's further away, it travels slower. So in a certain amount of time, it goes from here to here. And let's call that time T1. That time could be anything. It could be 1 week, it could be 2 weeks, it could be 3 weeks. It's just T1. The planet travels slower because it's further away from the sun, so the force of gravity is weaker. And Kepler said, if you were to draw out, if you were to sweep out an area, you would get a triangle that looks something like this. And he then compared it to the planet's motion when the planet is closer to the sun. When the planet comes over to the left side of this diagram, when the planet is closer to the sun, does it travel slower or does it travel faster? It travels faster because it's closer to the planet, so the force of gravity is stronger. The planet travels faster, and so in the same amount of time, T1, the same time T1 may be 1 week, 2 week, whatever the case may be, but the time is the same on both sides of that diagram. It covers a longer distance, covers more distance. So if you were to sweep out an area by drawing a triangle, let me draw it in a different color. That'll help. I'll draw it in orange. this area, the area of this triangle in orange, will be equal to the area of the triangle in purple. That's a very important thing he said. He said that they're going to have equal areas. Now, the reason why they have equal areas is because these two triangles they're basically triangles laying down on their sides. One triangle's base is less than the other triangle's base, but it makes up for the height by the height. And the reason this is because the planet travels faster when it's closer to the sun, and then it travels slower when the Earth is further away from the sun. So this is Mr. Kepler's third law. This is Kepler's third law. This is the second law. I'm so sorry. This is Kepler's second law. I said third law? Sorry, this is Kepler's second. All right, so can we look at Kepler's third law? What? What's that? We were what? For the second law, you draw the diagram and you say that if the times are equal, the area that the planet sweeps out on the right side and the left side are going to be equal to each other of the diagram. The areas that the planet sweeps out are going to be equal. The other thing I would put down for the second law is that the planet travels faster when it's closer to the sun and it travels slower when it's further away from the sun. All right, so third law. Does anyone remember what Kepler's third law is? Mr. Kepler's third law. Xavier's got it. He talked about something called period. What is period? Just the amount of time. The amount of time to do what? Time to make one complete revolution or one complete cycle. Time to make one complete revolution. I'm going to run out of room, so I'm just going to write down rev. You should write down the whole word revolution. So one complete orbit. One complete revolution or one complete orbit. Or one complete cycle, whatever you prefer. Now, in physics class, they use a T for period, capital T. That's physics class. What do they use in your astronomy textbook? They don't use a T. What letter do they use? What variable do they use instead of a capital T? It was a P. Exactly, it's a P. For in the astronomy textbook, they don't use a capital T, they use a P. So I'm good with either, okay? Either is fine with me. What Kepler said, so you can use T or P. In fact, I'll write it down for both. Kepler came up with a relationship. He said that the distance between the planet and the sun, the semi-major axis, or the average distance between the planet and the sun, he came up with a relationship between the distance and the period. He said that the period squared is equals to the distance cubed. A stands for the distance. A is the distance between the planet and the sun. Distance between the planet, or the average distance between the planet and the sun. So in astronomy class, this is how you would write Kepler's third law. He said, look, there's a relationship. p squared equals a cubed. In physics class, you wouldn't write it as p squared equals a cubed. You'd write it as t squared equals r cubed. So this would be in physics class, because in physics class, period is written as a capital T and distance is written as an r, because the distance between two planets ends up becoming the radius, because one of the planets ends up rotating around the other object. So the planet rotates around the sun. So this is how they write it in physics class, because they use t for period and r for distance. This is how you write it in astronomy class, because in astronomy class they use p for period and a for distance. A is the average distance between the planet and the sun, or it's the semi-major axis. Cool beans? Can I erase? All right, so let me just check one thing. Perfect. Okay, so Kepler's third law, I'm just going to add to it. They didn't mention this in your physics, in your astronomy textbook, but you can also use it to compare two planets' motion around the sun. You would just call it planet A and planet B. If you want to compare planet A and planet B, so planet A is Earth around the sun, planet B is Mars around the sun, right? He came up with the relationship that P, planet A period, planet A's period squared over planet B's period squared is equals to, sorry, did I say planet A's period? Yeah, squared, okay. Planet B's period squared is equals to their planet A's distance cubed, planet B's distance cubed. So this is a comparison. If you're comparing planet A and planet B, and you have planet A's period and you have planet B's period, and you have planet A's period, planet B's period, meaning the time it takes to make one complete revolution, and you have planet A's distance, then this is how you can find the remaining variable, whether that variable is the distance of B or the distance of A or one of the periods. If you have three of the four variables and you're comparing data between two planets, you can use this equation to find that fourth unknown variable. So this is how they write in astronomy class. In physics class, you'd write it as this: TA squared, TB squared, RA cubed, RB cubed. Which do you prefer, by the way? Do you prefer the T and the R or the P and the A? P and the A? Paul?
Yeah.
Cool. Okay. And that is Kepler's three laws. Any questions on Kepler's three laws? All right, so when Newton came around, he took a different version on Kepler's laws. He took a different version on Kepler's third law. He took a slightly different take on Kepler's third law, a different perspective, where he added mass to it, the mass of the planet. And that's going to be part of your reading in section 3.3. Part of your reading in section 3.3 is what I've already covered, but part of it is going to be about Newton's take on Kepler's third law, the law that we're just now working on. But Newton, when he came into the picture, he said something very important. He said